Hello, and this is going to be the second to the last part of Unit 3 on plate tectonics. First one we talked about Alfred Wagner, and then we talked about Earth layers. And now we're going to talk about lithospheric plates and how they actually move around the coast or the surface of the planet, making coastlines for continents, and some called passive and some called active margins, which we'll talk more about later. But basically, plates do the same thing cars can do. You can back them up and then drive them away from each other in opposite directions. You can drive them in opposite directions toward each other, or you can drive them in opposite directions right side by side. And these are called divergent, convergent, and transform, or um, well, we'll talk about earthquakes a little bit later, which we've already sort of talked about. But basically, we have the expansion, the compression, and the shearing forces, tension, compression, and shearing forces, which actually cause these earthquakes. They give rise to a three-dimensional picture of the Earth where we get divergent, usually happening in the middle of the ocean ridge, actually making mid-ocean ridges. Um, Making a rift zone down there where molten rock is moving out, and this is subjected to different ages on both sides and different magnetic reversals on both sides, which we've talked about already. Eventually, since the Earth isn't getting any bigger, it moves over, if it's oceanic, it moves into a continental rock where it gets subducted down. This is the divergent boundary where it goes down, it melts, and eventually mixes in with the molten rock in the mantle. But it also produces molten rock that does not like to be down. It's actually less dense. It moves up because it's hot. It burns through the crust and makes volcanoes on continents. We also have oceanic crust pushing continental crust into other continental crust, and it actually is another divergence, but we don't get any subduction here because we've got these nice lithospheric plates that are made out of mostly felsic material, light dense material, and it does not go down. And then if you notice right here where we have these divergent area and a divergent area here, so this rock on this side is moving this way, this rock on this side is moving this way, but right here that rock is moving the opposite direction, and this is where we get the shearing forces. San Andreas Fault in California is one of these, where North America has actually moved right over the top of an older mid-ocean ridge, and that shearing force is actually moving California in two different directions laterally. This is an animation that I've already made a shockwave, and if you want to know more about this one, you can actually click this link, or what you can do is you can actually look at the Pangea activity. But basically, if I was to click this very quickly, if we just go to the animation, and if you watch it, Pangea breaks up north and south, giving us Laurasian Gondwana, moves over to the way the continents are today, and then 50 million years in advance, you can see the Mediterranean Sea gets smaller. North America and South America may separate, but it moves farther to the west. So it's got lots of different things. Okay, so let's go back into here. This is another shockwave which actually talks about earthquakes, normal faults, where basically if you take a look at this, the hanging wall moves down, and that's a normal motion. Reverse fault is where you get compression, and then actually that normal fault, this one is actually caused by tension when you pull the plates apart. Reverse fault is actually caused when you push the plates together and the hanging wall moves up. That's the reverse of normal. And a strike slip is when the motion of the plates moving in opposite directions in that direction. You can access that through this shock wave, or you can just type in volts VF SWF and you can see that. I think I have that up on our webpage also. Divergent plates, these are plates that move apart. They move away from each other. Divergent means to move apart. This happens at what's called the mid-ocean ridge. This is where we get a rift zone. Rift zones are actually, when you rip the Earth apart, it fills with upwelling magma. It tends to be mafic magma, oceanic crust mostly. Early separation produces a very narrow linear sea, and that's like the Red Sea. And if it gets later and longer, it actually goes to a wider ocean like the Atlantic Ocean. This is a picture of a moving lithospheric plate being pulled apart. Magma moves up from the asthenosphere up and actually produces volcanism, although it's over a much longer area, and it pushes these plates apart. creating the different ages on both sides symmetrically, and also the magnetic reversal pattern on both sides. Rates of spreading, it's faster in some areas than other areas. This actually, if it is a faster spreading rate, it gives you a much broader, much more gently sloped mid-ocean ridge with less intense earthquakes. Slower speeds give you narrow mid-ocean ridges with more intense earthquakes. This would be like the East Pacific Rise off the coast of South America in the Pacific Ocean, and this is more like the Atlantic, the mid-ocean ridge in the Atlantic. So if we take a look, you can actually see here's the East Pacific Ridge, and it's moving at 185, 161, 110, 73 centimeters, and you can see it actually gives rise to a very broad area of divergence. And here's the Mid-Atlantic Ridge, 37, 40s, 25s, a much more narrow mid-ocean ridge. So much more broad, gently sloping, and shallower, and less more often earthquakes, and these actually give a little stronger earthquakes but a much steeper, much more narrow mid-ocean ridge. But this whole red area that you see here, even going up into some land masses, and you can see some other ones which we'll talk about before, and this is actually back arc divergence and back arc divergence, but we actually have a very long mid-ocean ridge that pops off and comes back on the map there. Convergent areas, by definition, actually is when two plates move together, and we can have an oceanic-continental convergent, we can have an oceanic-oceanic convergence, and you can have continental-continental convergence. But anytime two plates move together, ocean floor is usually destroyed at this location. You can see it actually moves. There's the oceanic crust being pushed down into the mantle, where it's going to melt and cause volcanoes on the continent. Two oceanic plates. The oceanic plate, so one of them, the older one, the thicker one, the more dense one, actually is convected down. So it's a convection zone, subduction, same sort of thing, except now the volcanoes are on water. And this one we don't have oceanic crust, so we don't actually get oceanic crust destroyed in this one, and this is why it's only done in most of them. An earthquake zone, this one actually may have the deepest earthquakes of all, and they can go all the way down to 670 kilometers, and that's basically where the rock actually gets too soft and it no longer moves. But it produces shallow earthquakes, intermediate earthquakes, and deep earthquakes. We can have oceanic-oceanic convergence. This is when or oceanic-continental convergence. This is when oceanic plate is subducted down underneath the continental crust. It creates what's called a continental arc, or a volcanic arc. Has andesitic, felsic type, and mafic type mixture volcanoes, which tend to be the most dangerous or most destructive, but also the most cool ones to watch in videos. Explosive volcanic activity. Mount St. Helens is an example of this, where the Juan de Fuca Ridge in the Pacific Ocean is actually moving the Juan de Fuca Plate and the Pacific Plate, but the Juan de Fuca Plate is actually moving under North America. This is Washington State, and it actually goes down, melts, and the material that's up at the surface does not like to be down here in the mantle. It is less dense. It's also hotter, so it's less dense. It burns through the continental crust and actually produces Mount St. Helens, which erupted back in May 18th, 1980. Very, very, very well publicized and photographed, and movies of that volcano if you want to see again. Mount St. Helens, 1980. We can have oceanic-oceanic convergence. This is when we actually get an older, more dense oceanic crust being subducted down underneath a not so old, not so dense oceanic crust, and we get the same sort of thing. We get volcanoes, but now they're popping up out of water. Now it's called an island arc as opposed to a volcanic arc, and they're basaltic volcanic rocks, so they don't tend to be as violent, although there is some granitic material that washes off the continent that actually makes what's called a geosyncline down here, which can get into this whole process, especially if it's on this side, and it can actually produce felsic and mafic, again making fairly destructive volcanoes. So here's an example of oceanic-oceanic convergence, and we get these volcanoes of the Aleutian Islands, we get the volcanoes of Japan, get the volcanoes of Vietnam, all the islands out in the Pacific. This is a hot spot. This is a little different. And then we have another one that's located right up in here, right off the coast of Washington State, and that's what actually produces all these volcanoes you see here, including Mount St. Helens, which they're not showing Mount St. Helens, but uh, Seattle, Washington is right here, and you can see Mount Baker. But you can see there are some earthquakes, and you can see there are volcanic eruptions that have gone on, all because the Juan de Fuca plate's being pushed up underneath the North American plate. North American plate being pushed from the mid-ocean ridge in the Atlantic Ocean, going this way, and the Juan de Fuca plate being pushed away from the Juan de Fuca ridge, going this direction. And eventually, North America will move right over the top of the Juan de Fuca plate, just like California has already done, and will actually produce this faulting, which California has here, Los Angeles being on the Pacific plate and San Francisco being on the North American plate, will eventually be suburbs of each other, not because it grows, but because Los Angeles is moving sort of this direction, San Francisco is moving sort of that direction. You can also have continental-continental convergence. This is when we get two continental plates going. And here we have a little bit of a problem because the continental crust, regardless of which side it is, does not want to be subducted down. So what it does, it just plows underneath the other continental crust and pushes up the continent and creates a very large mountain range, like the Himalayas in India and Nepal, to forms rock much more than all the rest of them. So here is an oceanic-continental, here's two oceanic plates, and here are two continental plates. You can see there's volcanism, no volcanism. We actually have oceanic crust dying, and continental crust basically stopping and doing most of the deformation, although no volcanism. Last plate margin we got to talk about is transform fault, and these are when plates move past each other. Between segments of the mid-ocean ridge. Oceanic transform faults are perpendicular to the mid-ocean ridge, and continental rock transforms faults across continents. So if you take a look, here's the mid-ocean ridge, the divergent. There's another part of the divergent, and the reason it's broken off, if you ever try to break an egg, it does not break on a nice smooth surface. Breaking a spherical object actually gives you this zigzag pattern, and if you were going to move those eggs around, you'd actually get these divergent areas, and you'd also get these transform. All these plate boundaries have rock moving in opposite directions. If they're moving away from each other or moving side to side is the difference between divergent and transform. So here's the mid-ocean ridge, there's the other take of the mid-ocean ridge, and we have a transform fault in between. This is called a fracture zone. Because this plate may be moving a little faster or slower than this one, you may get fractures, but you're not going to get the transform fault because they're basically moving in the same direction. This is another one which I've got loaded up on our Fusion page or our YouTube page, showing the motion of the transforms, and I'll actually show you the difference between divergent boundaries, convergent boundaries, transform, and plate tectonics. And I do want to show this to you really quickly. I don't want to spend a lot of time doing it, but a divergent area where two plates move apart, mafic rock comes up, makes new mafic rock, and depending on the magnetic reversals, we'll actually record that. Convergent areas where two oceanic plates moving together. This is an oceanic-oceanic convergence making a volcanic arc, except now it's making islands, so we call them island arcs. This is a transform fault. This one is not on the ocean floor. This one's actually on dry land and producing earthquakes. And we can have shallow and intermediate earthquakes in this one. We actually have shallow, intermediate, and deep earthquakes. And this one we only have pretty much shallow earthquakes. And there's the whole idea of plate tectonics, and I'll be doing a movie on this one as well, although I think it's probably, since it's in this one, I was going to do it here, but since it's in this one, I may have already done it. So I'll take a look at that video, but I think I explained this. And if you take a look at the plate boundary, which one is it? If you take a look at the plate motion video that's on there, I'll explain that one, I think, pretty well at that point. Okay, so here's the mid-ocean ridge. There's a transform fault. There's the mid-ocean ridge. There's another transform fault, and you can see this zone is moving in between San Francisco, Los Angeles, and all the way into this Baja California area, or the Gulf of California, making the San Andreas Fault, and you can see it actually can separate property values. But it is a transform fault, so there's one fault actually moving this direction away from that mid-ocean ridge, and there's one actually moving this way from another ridge that's down here. Okay, so there's another video which I'm going to talk about, and it was actually in that plate motion, but basically it's showing you the divergent areas and shallow earthquakes and convergent areas and deeper earthquakes and oceanic-continental convergence, where we get that molten rock moving up and producing volcanic arcs. It doesn't really show you the other, well, it does have a transform fault right there, and then we have fracture zone. Older rock moving that way and older rock moving this way, except the rock gets older on this side because this side it gets moved back down. And the moho, which is actually the barrier between the crust and the upper mantle, except if we take the crust and the upper mantle, these are the lithospheric plates. Earthquake depth and type. If you actually take a look at this map of earthquakes, we have shallow earthquakes showing us in yellow, and we can see there are lots of earthquakes in North America. We're located right about here, and we do have earthquakes, but nothing close to what they have out here in California. The blue ones are intermediate earthquakes, so you can see we actually get those at mid-ocean ridges. East Pacific rise, which is over here, not quite as many blue as we do get in the Atlantic mid-ocean ridge. But then we take a look at these subduction zones, and we actually see shallow, and we see intermediate, and we see deep earthquakes. And if you think about a basketball, and you think about a surfboard moving over one of these little depressions in a basketball, that depression is what actually happens to the plate as it's being subducted down. So here's the plate, and then it gets subducted down, and here comes North America or South America over the top. And if you take a look, the shallow earthquakes are there. A little deeper they get intermediate, and then they actually, a little farther away, they get deep. So we can actually see that this plate, which is called the what that plate's called, but this plate's actually being subducted under South America, and you can see that it actually hits right about there, and then we get deeper earthquakes and deeper earthquakes, but it actually shows us that this plate is dying. If you take a look at this plate is the one that's going down, this is the plate that's going down, that's the plate that's going down, this is the plate that's being pushed down because it's shallow, intermediate, and deep earthquakes. Same sort of thing, this Pacific plate is dying here because there's the shallow, intermediate, and deep earthquakes that you see over there. And then we have islands being created out here, and we have volcanoes being created all along this area, and actually that's volcanic arc. If they actually get a lot of volcanoes happen, or if they get very large and they start coalescing, touching each other, then we call it a mature island arc, and that's like Japan. It's like other islands that are out there, the Philippines. It's also like the Aleutian Islands, at least the beginning part of the Aleutian Islands. You can walk out to some point out here, and then eventually you got to take boats out to them. And that's the end of this video, so I appreciate you stopping by. We'll talk about 3-4 really soon. Please, if you wish, take a look at some of these videos which I'm actually showing you with these shock waves, because I think it'll actually bring out a whole lot more material and maybe make you understand it a little better. But I do have other shockwave videos up on our website. Thank you much. Bye.